Welcome to Chapter 3, Scaling Relations and the Volcano. Chapter 2 handed us a machine. Feed it 4 adsorption-free energies, and it returns a theoretical overpotential. The obvious next move is to turn the crank on every surface you can imagine and keep the winners. That plan runs into a wall almost immediately. 2 of the 3 intermediates are not free to be whatever a chemist would like. They are bound to each other by a regularity so stubborn that a floor appears underneath the overpotential of every catalyst obeying it. We will derive that floor rather than quote it. Look at how each intermediate attaches. The OH species sits on the surface through a single oxygen atom with a hydrogen hanging off it. The OOH species also sits through a single oxygen atom with an OOH tail hanging off it. A surface's chemistry, from an adsorbate's point of view, is largely how strongly it grabs one oxygen through one bond. Make the surface more oxyphilic, and it grabs harder on both. So the 2 do not respond independently. They move together. Bare adsorbed oxygen is the exception, because it binds through 2 valences and responds about twice as steeply. Compute both energies on surface after surface, across different metals, oxides, facets, and coverages, and plot one against the other. The points do not scatter freely. They fall close to a line of slope 1, displaced upward by a roughly constant offset of about 3.2 electron volts. Treat that number the way this series treats every empirical input. It is an approximate regularity with real scatter around it, useful because it is robust, not because it is exact. Roughly 3.2 is the honest precision of a trend, not a constant of nature. Nothing here depends on the 3rd decimal place. Here is why the relation is bad news. Chapter 2's 4-step energies looked like 4 independent design variables. They are not. The second step is the adsorbed oxygen energy minus the OH energy. The third step is the OOH energy minus the adsorbed oxygen energy. Add them, and the adsorbed oxygen term cancels. Their sum telescopes to exactly the quantity the scaling relation pins down. 2 of the 4 steps have been welded together. You may slide energy between them by moving the bare oxygen intermediate, but you cannot reduce their sum. 2 degrees of freedom have quietly disappeared. Now the arithmetic, and it is short. If 2 non-negative numbers have a fixed sum, the smallest their maximum can be is half that sum, achieved when they are equal. The 4 steps must add to 4 times 1.23, which is 4.92 electron volts. The welded pair sums to 3.20. So the best any obedient catalyst can do is split it evenly, giving 1.600 electron volts. Subtract the equilibrium potential, and the floor is 0.370 volts. A brute force scan over 320,000, and 1 splits finds nothing better. The inverted question is the sharpest way to see the problem. A perfect catalyst needs the offset between the 2 singly bonded intermediates to be 2 times 1.23, that is 2.46 electron volts, so both welded steps can be exactly 1.23. Nature appears to offer roughly 3.2. The gap of about 0.74 electron volts is the entire problem of oxygen evolution catalysis, stated as one number, and it is a chemical target. Closing it means changing what the offset is, not how carefully a surface is optimized. Now collapse everything onto one number per catalyst. The descriptor is the adsorbed oxygen energy minus the OH energy, which is exactly the second step. Because the scaling relation already fixed the sum of the middle pair, the third step is forced, and the limiting step is the larger of the 2. Sweeping the descriptor, using illustrative teaching values on fictitious surfaces, gives 2 branches. On the strong binding leg, over-stabilized oxygen is expensive to convert, and step 3 limits. On the weak binding leg, step 2 limits. The apex sits at 1.60 electron volts. Here is that sweep in code. One function returns the limiting step, a second returns the overpotential, and a scan over 400,001 grid points locates the apex numerically. The numerical apex matches the algebra to 5 decimals, at 1.60 electron volts and 0.370 volts. The whole curve then has a closed form. The overpotential equals the floor plus the distance from the apex, verified across the scan to about 2 times 10 to the minus 16 volts. Misplace your descriptor by 0.3 and you pay 0.3. The volcano is sharp. One caution, and the code states it explicitly. Steps 1 and 4 are not on the descriptor axis at all. They depend on the OH binding energy itself, and the scaling relation ties them together too. Their sum is 1.72 electron volts. Neither may outgrow the welded pair, which brackets the OH energy inside a window. At the apex, that window runs from 0.12 to 1.60 electron volts, a width of 1.48. Comfortable, which is why the picture works so well in practice, but it is a window, not a guarantee. Step back and look at the shape of what just happened. We began with a 4-dimensional problem and ended with a function of one variable, and the reduction was neither an approximation nor a fit. 2 constraints, one thermodynamic and one empirical, each removed a degree of freedom. That is the descriptor idea, and it is the most transferable thing in this chapter. A descriptor is one cheap number that predicts an expensive one. It buys screening, and it buys interpretability. It costs generality silently. Feed it a surface that breaks the relation, and it answers confidently, wrongly, and without warning. Let us recap. The OH and OOH intermediates both attach through a single oxygen, so they respond together, offset by roughly 3.2 electron volts. That welds steps 2 and 3 into a pair whose sum cannot be reduced. From the fixed total of 4.92 in that weld, our code derived an overpotential floor of 0.370 volts, confirmed by brute force, and showed a perfect catalyst would need an offset of 2.46. The apex sits at 1.60, and distance from it converts 1 for 1 into overpotential. Next, hands-on screening in Python.